Log on, tune in, find out. Another good idea from Cambridge.
Okay, so welcome back to the second part. And so I want to talk a little bit on reconstruction techniques, but of course will not give an overview of all possible methods how to reconstruct Q from the far-field pattern, but just want to sketch two approaches which use the Lippmann-Schwinger equation here, or one really very popular methods. And the Born approximation is not only used for the reconstruction technique, but it's also used a very popular model. It's also based on the here on the Lippmann-Schwinger equation. Recall that U is the total field, that is the incident field, K is the wave number, Q is the contrast function which vanishes outside of D. And this is an integral equation with respect to U, and phi is the fundamental solution of the Helmholtz equation. If you, this is a fixed point equation. You see, you search for a fixed point of this operator here, respect to U, and a natural way would be, and that is very popular in the engineering literature, that they kind of iterate this fixed point equation. So, and as a mathematician, we know that this fixed point iteration for an operator does not always converge. It converges if the norm of this operator, is strictly less than 1. So you see that immediately here. That gives you the norm of that operator is less than 1. That gives you kind of conditions on the smallness of K, or the smallness of D, or the smallness of Q, but kind of a coupled, you can, it's an exercise to compute the norm, say with respect to the uniform convergence, with C infinity, C0 infinity norm, what the norm of this operator is. So the first iteration in this scheme would be that you substitute the incident field for the total field. The total field is incident plus scattered, so you ignore the scattered field. So this is the first iteration, and I call that Born approximation, or that is called Born approximation. So with a B here, the Born approximation, the total field is the incident field plus this, where now here the incident field gets in. So this is the scattered field for the Born approximation. So you see the scattered field is just this, and so the scattered field can be explicitly computed. You know the incident field. Here I again denoted the dependence on the incident plane wave here, and if you substitute, if you look at the far field pattern now, then you look again. The asymptotic behavior of the fundamental solution here is given by that, and so you get as a far field pattern this, and if you insert the incident field is e to the I k theta times y. Then you see you get this simple term here. And furthermore, you observe this is the Fourier transform here of Q. If you extend Q by 0 outside of D, then you get K squared times the Fourier transform of Q, and you evaluate the Fourier transform at K times theta hat minus, or x hat minus theta hat, depending how you define your Fourier transform. Maybe there's also a constant there that is a matter of definition of the Fourier transform. So in the Born approximation, the far field pattern is just essentially the Fourier transform of Q, and here as an argument you have K times x hat minus theta hat. Okay, and so the inverse problem here would be determine Q from the Fourier transform, but you know the Fourier transform only for K theta hat minus this, and this lies, if you a simple observation, this lies exactly, or this fills the ball of radius 2k. Yeah? So here you see again the ill-postedness of the inverse problem. You have given the Fourier transform on a finite ball, and you want to recover the function. So the Fourier transform, or the inversion of the Fourier transform on a ball, that is also an ill-post problem with exponential ill-postedness. And also you see you expect better results if k becomes large. Then you have it on a bigger ball, and then it should be better. On the other hand, if k gets large, then the Born approximation is not valid anymore, or at least there are problems there. Okay, but this is I want to discuss the Born approximation, because now before we come back to this Born approximation when we look at the factorization method. The second one is just the iterative methods. That's the way Rainer Kress' talk yesterday went into this direction, but now it's here for the inhomogeneous medium case. You consider just the mapping, which maps your contrast function Q into the far field pattern, and you want to solve T of Q equal F. F is kind of a given measured far field pattern, and you want to invert this nonlinear map. Okay, so there are of course plenty of methods how to solve nonlinear problems of that kind. So I just mentioned here Newton type method, gradient type method, second order methods, but all of them need the derivative of this operator, in the direction of h, and you can also write down what the derivative of that is. And but here you see again that the derivative is compact and one-to-one, so you have to regularize this. So this is an ill-post problem, linear problem, and also this is ill-post, and you have to regularize that. We will learn later on from Samuli how to do that. But setting up this problem here in function spaces, you have to work with, or you have to study regularization methods in infinite dimensional spaces, and there are criteria when these regularized iterations converge. But if you look at the assumptions, then people could not prove it for this for this application. So there's a gap between the general function analytic regularization of nonlinear equations, nonlinear ill-post equations, and these applications here in inverse scattering still. So the advantages of these iterative methods are very general, of course. I mean, every inverse problems you can formulate in this way. I mean, Samuli did that, and you can apply these kind of methods there. So you can also incorporate a priori information. If you know that Q is positive, you can build that in. Disadvantages, certainly it's very expensive. I mean, you have to solve a series of forward problems. Maybe this forward problem is not so difficult to solve, but I mean, if you look at Maxwell equations or so, then solving one boundary value problem for Maxwell equation, that is a big challenge already, and many groups, research groups, who concentrate just on that. And here we have to do it for a sequence of that. So it's very expensive. That is what I mean, expensive. Also, Newton method, only local convergence can be expected, so you have to have a good initial guess for that. And also, as I mentioned, no rigorous convergence result in this is known. I mean, there are exceptions, but in principle, I would say so. Okay, now I come to the third part, and that is where the factorization method gets in. The sampling methods take a completely different view. But first of all, I mention it here, they only determine the support of D, not Q itself. That is certainly could be considered as a big drawback of this method. But in many applications, you only want to know where does the contrast or the index of refraction differs from the background. The idea in general is you choose a set of sampling objects, for example, points, Z in RD, and construct a binary criterium, which gives you yes or no, which depends only on the data you have, to decide whether or not this point Z, in this case, belongs to D or not. So now then for every point, you put a grid in your space around the region where you expect D to be, and then for every point you get this fast answer inside or outside. And then you plot those who are inside, and yet you get a picture of your region. So this is the idea of all these sampling methods. So some members of this group, the linear sampling method, they use these points, and I will talk on the factorization method. The probe method by Ikehata, it uses curves coming from somehow infinity or so, to 1, and you test with curves and have a binary criterion on that, and decide whether or not that curve, the endpoint of that curve, touches the unknown object or not. Then the no response test by Luke and Potters, they use domains to sample, domains which are inside or outside. Singular sources method also points in combination with the point source method. We will only discuss the factorization method here. The advantage is it's very fast. It avoids the computation of direct problems. So we also avoid the inverse crime Samuli mentioned, because the method is completely independent and absolutely totally different from solving the direct problem. And big advantage is no a priori information on the type of boundary condition. So you don't have to know whether this is a penetrable obstacle, like in this case, or if you have Dirichlet boundary condition, or Neumann boundary condition, or impedance boundary condition. Even the type of differential equation does not have to be known in advance. I mean, we considered here in this talk the Helmholtz equation of that type. But you can think of also the equation in divergence form. So this times, say, 1 plus q u plus k square u equals 0. In R2, this corresponds to the E mode, that corresponds to H mode if you look at electromagnetic modes. So you don't have to know for the factorization method whether you have this equation or that equation. You determine the support of Q anyway. So that is a big advantage. And also, Q could be, the support of Q could consist of two separate domains. So you don't have to know the number of components of the support of Q either. So these are certain advantages, but of course, as every method has also disadvantages, and it's only fair to mention these disadvantages. So you have to have full information on the far-field pattern. The numerical results will getting worse drastically if you have only limited data. And it's not clear how to incorporate a priori information, and it's very sensitive to noise also. Because regularization, I must confess that so far I did not really understand why if you want to try to regularize this method, it always gets worse. If you do not regularize the method, it gives the best results. And I did not completely understand that so far. Okay, so the factorization method. Important is from the far-field pattern, which is a function of two variables, we go to the far-field operator. So we just take our data, u infinity, x hat, theta hat, as the kernel of an integral operator here. So you take any function g from L2 on the unit sphere and integrate with respect to theta hat, and that gives you this operator. No? So this is we call that far field operator. This is a far field pattern, and this is a far field operator. This is well known. This operator is certainly compact. You have a compact integration, and the kernel is smooth. And we assume that Q is real valued in my talk. I mean, I will concentrate on that part. And then F is normal in the functional analytic sense. That means it commutes with its adjoint. This, for me, it is very not surprising, but it's one of the very few applications of functional analysis where this operator is not self-adjoint, but it's normal, where you can really use the functional analytic properties of normal operators, and we will do that later on. And even more, if you take the identity plus this factor times F, that is a unitary operator. That is it's called the scattering matrix. Usually it's differently introduced, but in our settings it's just the identity plus this factor times F. It's a unitary operator, so S star S is the identity. And now this is a kind of an, and I want to go to the blackboard a little bit. F is 1-to-1. This operator, very explicitly given operator, is 1-to-1 if it's not if and only if it's if k square is not an interior transmission eigenvalue. And here these interior transmission eigenvalues come up, and next week there will be at least 2 talks on interior transmission eigenvalues, one by John Sylvester and the other by Fioralba Ciacconi. And here we have the interior transmission eigenvalue problem, so you can look at that without knowing anything about scattering theory. It's a completely independent topic now, but it comes up here. So you have 2 differential equations, both in D. This is the equation for a function u, and that is the original modified Helmholtz equation. And you have a second differential equation also in D, which is the unperturbed Helmholtz equation. So this corresponds to the incident field, and that corresponds to the total field. And on the boundary, the Cauchy data coincide. U equal W, and the normal derivative also coincides. Of course, U and W, if that is 0, then it is a solution. But if you can find k square, numbers k square, such that you can find non-trivial solutions, then this is called an interior transmission eigenvalue. And what you can show is that F is 1-to-1 if k square is not such an interior transmission eigenvalue, and that is very very easy to see then, because we have the far field pattern corresponds to the incident field. So here's the kind of the far field pattern, and here's the incident field. This is e to the I k x dot theta hat. So if you integrate that, multiply it by g and integrate that, then you have here fg, and that corresponds to the function g of theta hat e to the I k x times theta hat d s von theta hat over s d minus 1. So yeah, that's just superposition of that. So now how to prove if fg is 0, yeah, that means the far field so v infinity is 0, v corresponds to this as an incident field, because this is the far field of that. Then Rayleigh's lemma, we have seen that now, means that that is equivalent to that v vanishes outside of D. Here I assume that D is connected. Okay, that means that this function or I should write Vs, no? The scattered field there. That means outside of D, the scattered field is 0, so the incident field is the same as the total field. Yeah? So that means that on the boundary, the scattered field is 0. So you have V is the incident field, and also the normal derivative of V is the same as the normal derivative of the incident field on the boundary of D. And now you see the connection. V satisfies the Helmholtz equation in the interior of D, the modified Helmholtz equation, this one. And the incident field satisfies this equation inside of D. And on the boundary, you have that the Cauchy data coincide. So if k square is not an eigenvalue, then Vs and U incident, both the V incident and V 0, and that cannot be. That can only be if G is 0. Okay, so in a very natural way, the interior transmission eigenvalue problem comes up, and this is a topic of research by itself already now. And of course, you see that this is only a general case. You can take any differential equation, say elliptic, but Lassipé-Verinter extended it also to much more general operators. Yeah, you take a differential operator. Maybe here in this case you perturb it and do it without perturbation, and then you set up this eigenvalue problem, and then you want to prove, is a spectrum discrete? Do eigenvalues exist? And that kind of thing. Okay. So now we look at now we come to the factorization method, and first you look at the Born approximation. So we take the Born far field pattern in the Born approximation and call the corresponding far field operator FB. Recall what we had. We had an explicit form of the Born approximation. Yeah, I don't go back with the slides. You see what we had. The Born approximation was just this one up to, without the G, of course. No? So it was the volume integral Q, and here the incident field ik theta hat times y, and e to the minus ik x hat, that comes from the fundamental solution. And this G is there. Now we just interchange this integration and that integration, so then you get here your G, and that is e times ik theta hat times y, and you integrate that. Just changing the order of integration. This, by the way, is exactly this one there. You see that? There. We call that, this is an operator hg of y. Then you see here we have the operator h, y is in the region D, and the integration is over the sphere. If you do the adjoint of that integral operator, you have the integration over D, and you have to do the complex conjugate of the kernel, which is here. So you see that you have here direct and a factorization of that type, h star tb, h with tb is just k square is a multiplication operator with this q. I think it's very you can see that. So we have a factorization of the operator fb in this form. Now it's a factorization, and note fb is self-adjoint. This operator, if q is real, then this is certainly a self-adjoint operator here. I mean, so you see from here, or of course also from there, that FB is self-adjoint. The nonlinear F is only normal. So somehow you can directly see from the data whether the Born approximation is a good approximation or not. You check whether this operator is self-adjoint or not. No? If a Born approximation should be valid in some sense, then the discrepancy between F and F star should be small. Okay. Now let's compare it with in the discrete case. This was operator H. This was a matrix H, yeah, in the case of point sources. And you see the very analogous situation here. Yeah? A multiplication of that by a vector would be here a sum over the components times this. No? So you see the same very close connection here, and also the operator TB is just a multiplication operator, and the inner matrix Q is just a diagonal operator. No? So you'd also do kind of multiply by Q. No? So you see a very analog situation there. And so you have this factorization there and there. So, okay, now we go to that was a linear case, very explicit factorization. Now we go to the nonlinear case. It's a little bit more complicated, of course. First of all, we start with the incident with the field equation again, and we know the incident field satisfies the ordinary Helmholtz equation. So then you see that if you split U into U incident field and the scattered field, you see that the scattered field now satisfies an inhomogeneous differential equation, where k minus k squared q and the incident field serves as the source term there. You see that immediately. Okay. Now we define our operator H just as before. There was the same operator H. This is the operator H. H goes from L2 on the sphere into L2 on the region. So here my X is in the region D. So that is the operator H. Then, as I said, H star would be just here inverting integration and taking the minus sign there, yeah, and evaluating this on the sphere. And I also define an operator G, which goes now kind of back from L2 into on the domain into L2 on the sphere, because this is defined as a far field pattern of this solution. You see that the scattered field on the right hand side, the incident field is a spatial case of an arbitrary F. Here's minus k squared q incident field, and I allow here a special F. That gives me an operator which maps this F into the far field pattern of this solution. Okay. Now, what is that? Now, the far field operator, what does it do? You have our U is now the superposition with G there. So you have to superpose that, and you get, instead of the incident field, you get the superposition. So this term here. So that means you have that F is, you apply first the Herglotz operator, so you make this superposition of the incident sources. Then you get this, and then you apply the operator G, which maps F, which is now this, into the far field pattern. And that gives you the capital F. So this is the first factor of that. Now we look at H star. H star, H is given by that. H star is just interchanging order of integration. This is this. Okay, very explicit everything. So what you see, this is a far field pattern on the right hand side. This is a far field pattern for which, if you look at the volume potential here, So the volume potential comes in very naturally, although we do not use the integral equation method, but nevertheless, here is the volume potential, and if you look at, it is a radiating solution volume potential, and if you look at the far field pattern, the far field pattern of the fundamental solution is exactly this. So by superposition, this is the far field pattern of W. So you have that this is the same as W, the far field pattern there. Okay, so here it's again. And now we know already volume integral satisfies this equation. We had that before in a theorem. So we have that this phi there is just this. Okay. Now we recall what was G. Gf was V infinity, where V satisfied this equation, right? Now we put V, the perturbation of here, on the other side. So this equation is the same as this equation. We just put this term on the other side. Okay, now we compare this and that. And we see if we take as for phi here, just this term, then we have our W back. So therefore, if we take H star of this term here, we get our V. And that was our GF. Okay, and now of course we define this here as our T, operator T. Tf is k square q f plus V, where V satisfies this equation here. Then we have H star T is equal to G. Okay, now we substitute this G into this, into the previous, not so good, into here, and we get F has a factorization in this form, where H is as above, T is this, and V is the solution of that equation. Okay, so we have now a factorization of that. And if you compare that to the Born approximation, FB, so you had the same H as here, but T and TB, T is this, and TB was that. So also here, you ignore this term here, and you get back TB. So it's kind of also very natural that you get back the Born approximation here in the way. Okay, that is a factorization, but what's the method? Okay, you have an idea from the finite dimensional case. The link is now this theorem. We have to assume that the exterior of D is connected. D itself does not have to be connected, but the complement has to be connected. We cannot see holes in D. So for any Z, we define this function, which is again very analogous, I can't pronounce that word, in the finite dimensional case. But here it's a continuous function living on the unit sphere. Then a point Z is inside of D if and only if this function is in the range of H star. And that is without, I mean, in the finite dimensional case, we had to make some assumptions. Here it's very generally true. And I also want to go a little bit into the proof. H star, recall that it was his volume integral. And we want to show that there exists a phi, if at least if Z is inside. We want to solve this equation here. We have to solve this integral equation here for phi. Is that possible? Also kind of independent interest here. Both are far field patterns. This is the far field pattern of the fundamental solution sitting at Z. This is the far field pattern of the volume potential. So this equation is equivalent to this equation now, at least if X is outside the D and the point Z. Now look at first the case that Z is inside. Then you can solve this equation. Yeah, it's easy. You take the fundament, Z is inside of D. Z is inside. So you take a function phi tilde, smooth function phi tilde, which coincides with the fundamental solution outside of D. Yeah, but the fundamental solution outside is smooth because the singularity is inside, and you just extend a phi fundamental solution arbitrary inside the domain. You can do that by simply multiplying it with a modifier function there. And then instead of the fundamental solution here, you take the phi tilde here, and you can solve that because I mean this is this is a volume potential, and this is solved by the phi is the Helmholtz operator applied to the right-hand side. So that's a reason for Z inside you can solve that. For Z outside of D, this cannot be solved, because if Z is outside of D, say really outside of the closure of D, is easy to see, because then if you, this is a, say, continuous or at least bounded function on X everywhere, but this is unbounded if X goes to Z. If X is outside, there's no reason why X should not go to Z, so then the right-hand side is unbounded, but the left-hand side is bounded, so that can't have a solution. And the refined argument holds if X is on Z is on the boundary of D. I have to look into the right spaces there. Okay, so this gives you now a characterization of D by a range condition. And now we have this situation now. We have a factorization, and we have a characterization of the unknown D by this range condition. The problem here is that we don't know H or H star, because H star is an integral operator living on D, and we don't know D, of course. So the goal is now to express the range of H star by F. F we know. And this is right. So we have now a function analytic situation. Here I put it in a more general framework here for a moment. So we have two Hilbert spaces X and Y. We have an operator F which maps the Hilbert space Y into Y. Now this is the L2 on the unit sphere here, or far-field operator. H maps the L2 on the unit sphere into L2 of D. So that's another Hilbert space here, H. T maps X into itself, and H star maps it back. No? I mean, this situation we have, the diagram commutes. Okay, and now this is the problem. What can you say about the range of H star and F? Okay, we look at the first theorem, and this is kind of easy. If T, the operator T, is self-adjoint and coercive, self-adjoint is clear, and coercitivity is also clear, then the range of H star is the same as the range of the square root of F. I have to say a little bit about the square root of an operator, of course, but this theorem applies, for example, at the Born approximation case. Remember, in the Born approximation, the inner operator T was just a multiplication operator, and it is certainly a self-adjoint and coercive operator, provided Q is bounded below. And then you can apply the theorem, and maybe I have 5 minutes. I don't want to go further, but say a little bit, or is it clear to you how to prove that? that is everybody working in knowing the general linear theory on inverse problem should be able to prove that. First of all, we can that is maybe we can assume without loss of generality that T is the identity. If T is self-adjoint and coercive, then there exists the square root of T. Yeah? So T is of course not a compact operator, but self-adjoint bounded operator. There's a nice proof of constructive proof of constructing the square root of that operator iteratively. It's like a Newton type method of in operator notation. Yeah? So you don't need really spectral theory of bounded operators for that. Okay, so we assume that we can do that. Then we have the factorization is then of course in the form of T a half H star T a half H. Yeah, you have that. So you rename H to be that and that. So without loss of generality, T could be the identity. And then you have F is H star H. And what you do now is you consider a singular system. You all know what a singular system is, at least if you have had an elementary course on inverse problems. A singular system. So you have H psi j. You have two orthonormal systems. Assume that in this case H is compact, as in our application, and also H is injective, would probably good here. And H star maps phi j into the psi j. This is a singular system. The sigma j are positive. And then you see what is the range of H star. So a function, say psi belongs to the range of R. That is Picard's criterion, also known in the from this elementary proof. The Fourier coefficients or the expansion coefficients of my psi with respect to the singular system should decay fast enough. That is the qualitative, and quantitatively is that the Fourier coefficients of that, so if you have psi, psi j, these are the Fourier coefficients, and this should converge. That is the condition for psi being in the range of H star. Without this would just mean psi is in X or in Y, the Plancherel theorem, but if that decays faster than that, then you get the range condition. And if you look at F or F a half, psi, what would that be? You see, if you substitute this into here, you see that sigma square are the eigenvalues of F. So F a half would be sigma times the coefficients. So this would be F a half. F itself is sigma square, F a half is that. So if you look at Picard's criterion for this, you get exactly the same thing. So therefore, the ranges coincide. So for that case, it's kind of very, very easy to prove. And tomorrow we will consider the case where we are really interested in the case where T is not self-adjoint in the general case. But now is the perfect place to stop. Thank you.